Okay, so I think we can start now. People are still arriving, but we're going to start. So once again, thank you very much, Heng, for being here today. It's a great honor to have you for this talk. One small note about technical details. So you saw maybe the talk is going to be recorded, and Heng agrees for diffusing it to some people. So we'll see we will make the diffusion afterwards, but it's going to be recorded anyway. And so I'm very glad again to have you with us today. There are quite a lot of people, so there are two European research groups, ALPACA and PANGAIA. Two of them are focused on pangenomic problems. And so mapping sequence on graphs is a central operation for us. Sorry, I again authorize people to arrive. So Heng, I will make a short introduction of you right now. So you obtain your PhD in 2006, like I did, in China. And then you did a postdoc with Richard Durbin, who is here today, I guess. I'm not totally sure, but I guess he's here. Or if he's not here, he will have a look to the recording. Then you work at the Broad Institute before to arrive at Harvard Hospital Group in Boston, where you live today. And well, I'm not sure it's necessary to mention it, but you're one of the greatest creator of amazing tools in bioinformatics. So everybody know BWA, some tools, Minimap, 2, Mini-ASM, and now we're going to talk about waveform algorithms for mapping sequences on graphs. And so thanks again. Take all the time you need, and we are very happy to listen to you. Thank you.
Thank you, Pierre, for the invitation, and it is my great pleasure to describe my work here. And it's not going to be a long talk. Probably like 30 minutes each, I guess. And I don't know the exact time. But the outline is like this, and I will talk about give a background on sequence to graph alignment, and then talk about the wavefront alignment algorithm, this WFA, and then how to combine these two together, the sequence to graph alignment and the wavefront alignment, combine them together, basically this graph WFA. And in the end, I will talk about the bit integration into the mini graph. So far, the mini graph has the GWFA component in it. The reason that the GWFA is like Smith-Waterman is that the detail-based alignment for small sequences. But mini graph is like mapping arrays or assembly to the whole genome. And so this it's used the GWFA to do the difficult work. Okay, I'm going to the first part, the sequence graph. First, the definition, what's a sequence graph? And a sequence graph is basically, it is a directed graph. And for the moment, for most of part of my talk, I will only talk about more exactly the unidirected graph. The directed graph and with sequences labeled on the node, on the vertices, not on the edges. And it is also possible to label the sequences on the edges. That's a different kind of graph, but it's not as often used as this vertex level graph. And usually when we say vertex level graph, we often call it sequence graph. Although in theory you can also call that level graph as sequence graph, but we more often call this type of graph as a sequence graph. And so at the bottom shows an example. This each node is you have a directed graph and you have sequences attached to nodes. And so this you can spell sequences from the nodes from this graph. And then the sequence graph to graph problem is basically given this pairwise alignment, given a graph, sequence graph, and also a query sequence, a linear sequence, and you want to find the best alignment between the graph and the query sequence. And this is basically intuitively, it's like enumerate all the possible passes through the graph, and then do a pairwise sequence alignment, and then find the optimal alignment. Of course, I mean, in practice, we don't literally enumerate all the passes. And here shows an example. I mean, this is the same graph, and we have a query sequence. We want to align the query sequence against the graph. And then the optimal solution in this example is like you start with the TG nodes. You don't go into C. You go into the AG nodes, and then follow this edge, go into C and AG. And so the sequence built from the path, from the red path is this: the TG, the first node, AG, this node, and then C and AG. And you want to do alignment, the best alignment has two mismatches. This is the best alignment from the graph. And effectively, in practically, of course, we don't enumerate all the passes, but we want to achieve this effect. First, I will start with a similar problem. Is this partial order alignment? And in this case, okay, just a little bit. Here, the example shows the kind of the standard Smith-Waterman or global alignment. This is actually global alignment in this case. And this linear sequence, you have sequence 1 and sequence 2. And how we typically do that is when we calculate the score, when we fill the DP matrix, the dynamic programming matrix, and look at this cell, and we just look at these 3 nearby cells, and we use these 3 nearby cells to compute the score of this cell. And so we can extend it to a directly cyclic graph DAC. In this case, sequence 1, we turn the sequence 1 into a DAC, a direct cyclic graph. And so actually the procedure is actually fairly similar. And so when we calculate this cell, when we calculate the score of this cell, we always build this sequence. We always look at this column. But then when we look at the rows, it's we see which rows, basically each row corresponds to a node, which node can reach the cells in question. And in this case, we can get the both of these nodes and this node, this A and G can reach this. And so when we calculate, can consider the score, we will consider these 2 cells and also these 2 cells and also this number cells. We consider 5 cells in total. And with that, we can compute the score here. It's actually fairly similar to the linear sequence. In linear sequence, you can imagine there's an edge from C to A and an edge from A to T, etc. It's actually just extension. It's a fairly straightforward extension to that. And this type of alignment you also call it partial order alignment. Remember that in this case, the graph is cyclic. And so with the cyclic graph, we can do topology sorting. And so after topology sorting, we can visit all the predecessors. When we calculate, when we come to this node, we can calculate all the predecessors of this node before reaching this node. It's possible with topology sorting. And the caveat with the cycle graph is that one direct cycle, we can't calculate all the predecessors. For example, in this case, this graph, there's a cycle here. There's C, A, G, and then G come back to C, and then come to A. This is delta cycle. And so when we calculate when we calculate this say fill the dynamic programming matrix, we have the 0, 1. When we come to here, because we haven't calculated this cell. And so how can we calculate the number here? This is the main difficulty in cyclic graph. And so how do we solve that? I will come back to a little bit to it. And so first, give some the coordinate system in the following. Remember here in this graph, actually each node has only one base, and in most of our talk, it's actually each sequence each node has a sequence, not just one base. And we use this coordinate system. This the first base at position 1, and position 0 is reserved for a start symbol, special symbol for the start of the sequence. And the graph base, each base in the graph is indexed by V and J. V is basically the vertex, and J, remember this there's a sequence attached to a vertex, and so the J is the offset of each base. And again, the first base is 1, and so the query sequence is always indexed by I. And so on the left, this shows the the standard LED distance calculation, the standard dynamic programming calculation. And here the delta basically compared whether the two symbols at I and at J, whether they are the same. If they are the same, it's 0. If they are different, I mean, it's 1. The delta calculate that. And the sequence graph alignment, the formulation is actually only a minor extension to this one. You can see on the right, the first 3 equations is essentially the same as this one. You can see on the first 3 equations, when we don't change V, we don't change vertex, that is, we calculate the dp cells in one on one vertex, and this is identical to this one. And the only difference is the last equation, the last line. This is when j equals to 0, this is why we have this potential 0 reserved for special meaning. When we have at the beginning of a vertex, we actually we check all the vertex that can reach this this vertex. All the predecessors. This is U. Basically, U means all the predecessors of V. We check all the predecessors, and we just copy over the score. You can see there's we just copy the score here, and then the formulation is like this. And let's see how it works. I mean, this shows a example. And here, in this example, this again, this graph and this white space is reserved for this special symbol, the starting symbol. This is the coordinate 0, and this is called position 1, position 2. And here, for the sequence alignment, we only have one large DP matrix, and for this one, we split the DP matrix into several blocks. Basically, each vertex has its own the DP matrix. And here again, the first 3 equations, basically this is like the standard DP equations is only coming from these 3 nearby cells. And the last one, when we calculated this, it's starting this symbol, the position 0. We look at all this node can reach this node, and this can reach this. And so we need to look at this cell and this cell, and we compare which one of these is smaller, and then copy it here. This is how we calculate this start. This is just explain the formulation. But actually in practice, it's okay. Let me show this relatively simple example. There's no cycle in it. It is still a DAG, a cyclic graph. And so how that works is basically we have when we have this cell, and we can copy it over to the beginning of this cell, and copy it over to this cell. This is how the last line works. It's just copy it over. And so the question is how that work for the cyclic graph. And so it's important to note that this formulation is not for the algorithm. It's not for the solution. It's a formulation. It just give you the when you get the final answer, and this cell computes, the final answer will satisfy this equation. But you can't use this equation to calculate the cells, again, because the problem, because of the cycle. But then how we calculate that? What's the algorithm to fill the matrix? I will show you example. I suppose you have already filled the matrix for the first 3 rows, the TAA. And so here is the cycle, and you have already filled the first 3 rows. And I want to calculate this row, the G row. How do we calculate that? And so firstly, we don't we ignore basically we ignore the deletions in the cell. We only, when we know the previous row, you can use the previous row calculate this row. But unlike the full Smith-Waterman, we don't use the information on this row to calculate. And so in this case, for example, this 3, how we get 3 is there's a 2 here, and so we can have an indel from 2 to 3. And so we have 2 here because this G and G, this match. G and G is a match. This 2 coming from here. This 2 from 2. We get a 2 here. And similarly, we get 3. This is from 2 to 3, or from here. This is add indel from 2 to 3. But you see, when doing this calculation, I'm not using here. I'm not using say 2 to 1, or not using 3 to 2. I'm not using this information yet. And so I'm only using the previous row to calculate the next row. And of course, because we if you don't consider this row, all these ID distance will be larger than, not maybe larger than, than the truth. It may not be the optimal. And then the next step, we start to use we only look at this row to update the score. For example, here is we only use the previous row to calculate that. We get 3, 2, 3, 2, 1. And so when we start to look at, when we only look at the current row, because using the last line, and so this 1 here, and so we have copied 1 using this edge, copied 1 here. And so here the 2, we use this one. And it has 2 predecessors, 2 and 3, because 2 is smaller. And so we copy this 2 to here. And so when we get this, the next, we can see because is 1, and so this one should be 2 instead of 3, because 1 to 2, there's an indel here that is actually smaller than 3. And so we update the to 2. And once we update this one, actually we don't see other updates. And so this row is done. And so this way, this is the score at this row. And you can imagine that on a cyclic graph, this updating can take many rounds, but actually Navarro in 2000 proved that actually the total number of updates per row is actually bounded by, is linear in the number of vertices and the edges. And I'm not going to show a proof, but just intuitively, the initial score here will be just slightly larger than what is, than the real score. And so in practice, actually, you often don't need many updates, and you can get the final answer. And so this, and so because each row takes this linear time, linear in the number of vertices and edges, and so then you need to fill the each row, and then basically this quadratic time complexity, basically the length of the query sequence times the number of vertices plus the edges. This is how the sequence to alignment work. Sequence to graph alignment work is quadratic algorithm, and it works for cyclic graph. And so here the next section is this called Ukkonen's OND algorithm. This is the wavefront algorithm is inspired by this algorithm, and you will see later that it's actually the Ukkonen's OND algorithm is a special case of wavefront algorithm. And so here it shows the example, and this the numbers in gray basically this true IID distance between the two strings. And so with the Ukkonen's algorithm, with the Smith-Waterman, we typically fill the row by row. If we fill the full metric to calculate that. And with the Ukkonen's algorithm, we start with the 0, and then here is a match, G and G is a match. We basically extend along the diagonal. And so here, because it is a match, and so this cell must be also be 0, because the ID distance is 0, because you can extend it. And then once we, at this point, we can't extend it 0 further, and then we will touch the nearby cells. The nearby cells from 0 to 1, you start to add one edit. And so here in this case, it's from 0 to 1, because this is AC, this is a mismatch, and so you have 1. And so for this one, these ones are caused by indels, and so you get you get 1. And then the next step, similarly, you do extension. You can see from this one, because it's A and A is a match, T and T is a match, you can extend along the diagonal. And so this is one. And just do all the possible extension. After the extension, and similarly, you increase the edit distance by you mark the nearby cells has 2, and just just repeatedly do this. Once you extend 2, and then you come to 3. And so in this case, because it's 3, the C and C is a match, A and A is a match, you can extend these 3 to the corner. And so when we reach the corner, we know that this is the answer. And so if we look at the cells we filled in this process, we only fill this cell. We don't fill the full matrix. And so imagine 2 sequences are very long, but they are very similar to each other. Then we mostly just fill the diagonal. We actually don't fill the other part of the matrix. And so that's why it can be fast. And so the OND, this N means the sequence length, D means the ID distance. basically is bounded by the IDD distance. If the IDD distance is small, this algorithm can be much faster than Smith-Waterman, filling the whole matrix. It sometimes, for very similar sequences, it works on, say, megabase long sequences. You can get the answer in a matter of seconds. But with Smith-Waterman, it takes forever to compute that. This is the Ucker's algorithm. A little bit historical background. The IDD descent, Ucker found this algorithm in 1983 and published in 1985. And Jim Myers published essentially the same algorithm in 1986, but it has some extension, including a linear space variant. The original algorithm, if you want to calculate the detailed alignment, is actually you need quadratic space. And the Jim Myers has found the linear space algorithm for that. But computing score is the same. And then edit distance, but only after almost 20, this 40 years later, people find a formulation for IFN-gap. It's a lot harder. It takes 40 years to find it. And so this is in this paper, 2021 paper. This is how people name the IFN-gap version. They call it WFA wavefront algorithm. And the reason is that when we field it, it's you can see the three bound. It's like a wave. You have 0 wave, 1 wave, 2 waves, 3 waves. And so this is how they kind of intuitive name it like the wavefront algorithm. And then there are further developments. There's a reduced space, linear space version of the WFA. And here we also call this Ucker's algorithm as WFA because it's actually a special case of WFA. And also GWFA is actually not the really implementing the IFN-gap. It's just implementing the IDD distance, but still called GWFA. Okay. With these two algorithms, actually the GWFA algorithm is just a combination of the two. It's actually conceptually, it's actually not complex once you understand the previous two algorithm. And I will just show a example. How that works on this toy example. Again, this is the query sequence. This is this graph. And so we always put the 0 here. And so when we put 0 here and then do the first step to do the extension, we just extend the diagonal as much as possible. In this case, we can extend to this TNT this match, and so we extend to here this still at distance 0. Then we can't extend. Then we move to the next step. We just look at the things that's adjacent to the 0, and so here's 1. So this cell will have 1. This caused by gap. This is caused by a mismatch, A and G. This mismatch. We come here and then we do extension. And so the extension. Okay. Now we come to the end of the first node, and then we apply the fourth line, this one. We basically copy this 0 to we forward these things to the adjacent vertices. We fill the first column, the 0's position, and then we can still do extension from there. And so here we can do again extend along the diagonal. In this case, we can't extend, and in this case, we can, because there's this A is a match, A and A match, G and G match, we can still do extension. Now we come to the end of this vertex, and then we can still, again, the fourth line, we can copy this one to the next vertex, and still try to do extension. And so here, there's still a extension. This CSC, we can still do the extension. And when we come to the end, we copy it to the next vertex. And then now we can't do extension because T and A is a mismatch. We stop. This is filled out one cell. This is calculated the one wave. And so when we calculate the one wave, and similarly be the two wave, the cell with adjacent 2 will always be adjacent to 1. And so when we have the one cells, we just calculate all the adjacent one. This will be the two cells. And similar, this we get all the 2 cells, and then similarly we do the extension, and then finally we come to here. This is actually when we come to here. This is already the end of the calculation. Because we want to do here with this. We want to align the full query sequence against the graph, and now we come to the end of the query sequence, and so we know the added distance is 2. This finish the procedure. And then I see here we still haven't filled the full matrix yet. These cells are empty. We haven't come to this cell yet. And this is basically how the GWFA works. It's fairly similar to the WFA, and also the basically copying rule, mostly the false line, the special rule to copy the things over. It can extend along the graph for quite long. So there's a caveat, important caveat in the implementation. And if you look at the WFA, for example, this shows the example. We have this highlighted nodes. This is the wavefront. And so when here, when we come, say, when we finish the 2 cells, we want to calculate the 3 cells. We don't need to fill, we don't fill the D3, sorry. We don't fill the D3 here. The reason is that it is behind this two wave. And so it's if it's behind, you don't need to go into that. You can imagine if you go into this position, then the next position it will be 4. It will just be behind the wave. It will still keep increasing. You will do a lot of redundant work if you go into the diagonal that has been visited before. And so with the WFA is easy to check whether this 3 has been calculated or not. But with the GWFA, you can't easily to check whether this diagonal has been visited before, whether it is behind the wavefront, because between the vertices, this you don't know how the wavefronts are connected. You don't know how diagonals are connected, and actually this because there's the graph structure, and so sometimes one diagonal may have multiple predecessors because the graph structure. And so in practice, when we do the implementation, we have an actual array to keep track of the diagonal that has been visited before. And it's difficult to show it in the toy example, but for the implementation, that's important consideration. Otherwise, you will revisit like this. You will revisit the cells multiple times again. It will make the algorithm much slower. Also, we have the WFA has a heuristic to speed up the alignment, and so we also have this called the wavefront pruning heuristic. This similar in the similar vein, not exactly the same, but similar idea. The idea is basically to discard cells that fall far behind of a wavefront. And in this example, the furthest we call the front is the furthest if you can see there's an alignment length in it. And so this we call the furthest if the query length and the graph length in the alignment, this is sum. The query length is same, is 6, and the graph, the path in the graph, the length of the path in the graph in the alignment is still 6. So the 6 plus 6 is 12 is this cell. This cell is the furthest in the alignment. And so if you look at this cell, this is the query is 3, 1, 2, 3. The length is 3, and so the graph is 1. There's because when you align TAA to T, and so this the graph length is only 1, and so it is the sum of these two is only 4, and so it is intuitively it's you can reach the addition 2 with much longer sequence versus you can reach this addition 2 with much shorter sequences. Then it's more likely that the longer alignment is more likely to be the better one. It's more likely to reach the end position. It's more likely to be part of the optimal alignment path. And so in this case, we just get rid of these two. We just prune, we discard it. This is heuristic. There's a chance that these two may come to the best score, but this is heuristic, and it's quite effective in practice. It usually works. Okay, on the real data, this we mostly Howen prepared 4 data sets. There's a cyclic graph, 3 cyclic graph, and 1 cyclic graph, and this is not total number basis. We have the MLC here. The MLC is about 6 million base pairs, the number of vertices and number of edges. And in G4, although it's still the same MLC, it has fewer vertices because this is a mini graph. It doesn't contain small variants. Small, big differences. Only has some like structural changes between the MLC haplotypes. And this one, the G3, is the PDGB graph. It contains all the small even just a single base pair changes, it will, encode it in the graph. And so there are more vertices and edges. But as a result, the edit distance between the MZ haplotype 2 and GT4 will often be larger because, we don't have the small variance. And so this is the graph, and the queries, we have the linear sequence, we align to it. And in this table, this is different haplotypes. This shows the optimal edit distance. And the GWFA, this is without heuristic. GWFA pruning, this with the heuristic. And this destructure, this is another way to do the sequence graph alignment. The Navarro's algorithm, this is what we talked about at the beginning. And the graph aligner bit vector, this is a bit vector version of the Navarro algorithm. This is a more optimized, highly optimized bit vector Navarro algorithm. This column is exact. There's no heuristic in it. And the last column is graph aligner with heuristics. And you can see in this graph, it's the heuristics are always the fastest. And in all cases, the pruning algorithm, the heuristic actually gives the correct, the optimal edit distance. And again, the GT4 has a much larger edit distance because it doesn't encode small variants. And the GFI align, the heuristic graph aligner is faster than the exact GWFA, but it's worth noting that for all these red highlighted numbers, actually graph aligner doesn't produce the complete alignment. It fragmented the alignment. For example, because the edit is very large, and so this actually the alignment is not the best alignment. And the other algorithm, this algorithm all give the optimal edit distance, and because these are exact algorithms. And so a bit summary on the graph WFA is in practice actually implemented for bidirected graphs. It's a high considered the strandedness of the sequences, not just one sequence. It's actually easy to extend that to the bidirected graph. And as I said, it supports edit distance only, it doesn't support FNGAP. And the implementation doesn't follow the formulation here. It's similar, but not quite the same. Actually, I implemented WFA first, graph WFA first, and then Howen came in and actually reformulates the problem. Actually, much like his formulation than my original one. But this code still holds, so it's different. And so graph WFA is more like comparing, it's Smith-Waterman. You only compare very short sequences, and it doesn't work for whole genome graphs. And so when we integrate this GWFA into the mini graph supports the whole genome alignment. And this shows how then there's a lot of heuristics. This a few slides show how the mini graph heuristic works. And so here is a graph in red, and also a query sequence in green. And so how do we do that? First, we do seeding like minimap2. The first two steps, we pretty much minimap2. We ignore the graph structure. We treat each individual segment, each individual vertex as an independent sequence. And then we just do essentially that's minimap. We index with minimizers, and then do linear chaining with minimap2. We get the 3 chains. We don't consider this chain because there's only one seed. We consider it too weak. The random hit, and so we don't consider it. Then we get 3 chains. It's linear chains. And after that, we do graph chaining. When we do graph chaining, we only consider the distance between these nodes, basically essentially the reachability. Basically, we see if whether this node can reach actually this probably not quite right. It's actually it should be this one connected to this one, because the order is different. Anyway, you only look at the graph topology. It doesn't look at the individual sequences when we do the graph chaining. Once we do the graph chaining, then there will be gaps between the purple and the orange one, because we don't check the sequences. And then at this point, GWA comes in. It's connected to the two nodes with bases. And so here we do the GWA alignment to close the gaps. And then at the same time, we choose which is the best path. For example, in this case, we wouldn't choose the top because there will maybe it's too short, and we would choose the bottom, and then this we finish the alignment. And minigraph works for the whole genome. So just summary about how this is, we have a somewhat new formulation of sequence to graph alignments. I think this is, this not so much different from the previous one, but I think we put the sequences on nodes instead of the vertices instead of a single basis. This is more practical because in practice, when we implement that, we mostly deal with, this sequence-based graph, node-based graphs. And secondly, we have this GWFA. Actually, you can see it's actually fairly simple idea if you understand this GWFA and idea. And it is very fast when the edited distance is small. Even if the edit is a bit larger, but still you can see it's still much faster than the big vector highly optimized one. And it has been integrated into the minigraph whole genome alignment is now a component of that. And at the end, I want to thank Haowen Zhang. He is main contributor. He wrote the manuscript on the GWFA, and we work with and Srinivas is Haowen's PhD supervisor, and we all work together on this manuscript, especially on this theoretical analysis. And also, Shiqi Wu actually gave the initial implementation of the GWFA. I mostly kind of optimized that in C. Okay, that's enough of it. Any questions?
Thank you very much. I think we are all clapping. I feel a bit alone now, but thank you. It was really nice, really clear, and it's not that simple to understand just reading the paper. So your explanations were very welcome. We really appreciate. So I guess there are some questions. I have some, but I see that Paola has raised her hand. So Paola, hi. If you want to ask the first question.
I want just to thank Heng Li for the nice talk. I don't have specific question.
Okay. Sorry, I thought you were raising your hand for asking a question.
Yes, I just want to say that it was a nice presentation, but okay, I think it's better for somebody else connected to ask for questions. So
Thank you.
I have one question, actually, one technical question to start. I'm sorry if it's a bit naive, but there is something it's not totally clear to me. From your paper and what you explained today, it seems to me that your alignment, the original definition of the alignment, requires a starting node on the graph.
Yes.
For the wall graph alignment. So there is something,
Yes.
a link I am not able to do between the full query and a local alignment on the graph, which is what is interesting for us, right?
Because in this application, I'm actually only doing, you can see I'm closing the gaps. It's actually global alignment. I know the starting base and the ending base. I want to close the gap. So in practical application, I'm doing the global alignment. And it is easy to change the GWFA for the extension alignment. Basically, one end is fixed, the other end is free. It's easy to change that. And you can also change to, you can do local alignment. Basically, you don't know where to start. You want to align the full query sequence to the graph, but you don't know where it is. You can do this. We tried it. It's actually not that difficult to modify. It's more to change the initial condition. Okay, I'm now going to so far back. You can see, I started with this 0. That's it has the fixed starting point. And if you want to move it, you can just like mark out the top row as the 0, and then do extension. You can actually do that. But the problem is that that's actually make GWFA much slower, because it's because there's multiple this small edit distance. You need to fill quite a lot of area to come to the best alignment, parts. So we can do that. It may make GWFA much slower. Usually the WFA, I would say, is not the best algorithm for local alignment or local alignment because of that.
Okay.
It's not only applicable to the graph, it's also to linear alignments. WFA is usually not the best for that application.
Okay, thank you. As I do not see any question, I continue, but don't hesitate to raise your hand if you have any question for Heng. I have one about affine gap penalty. So it's feasible from theory, but do you plan to implement it in your algorithm?
Not in the near future. It's
Okay.
actually implementing that. It's this WFA, the affine gap WFA is already actually a lot harder than the maybe just show how can I find it. I think the key advantage, I mean, the simplicity in the adjacency that when you have one, you know all the tools are adjacent to one. I mean, you only need to explore adjacent cells, but that's not the case for the affine gap. Even linear gap, I mean, this you can have different substitution matrix. But in that case, I mean, it's not adjacent. You need to keep track of all this information, and that's actually quite difficult in the graph space.
Yeah.
I mean, of course it's possible, but as also it will become a lot slower.
Sure. Yeah. Okay, I have plenty of questions, but I wait for participants to raise their hand if they have some. No, not.
Is a question, I think, from Garance. I don't know.
Ah, okay. In the chat, maybe?
Yes, you can.
No, I cannot see
Can
it.
you see it?
No, I can't.
But we can ask him just to speak.
Garance, you want to say something? Or it's the old comment? Okay, we do not hear you. There is waiting for this question from Sergey, I think.
Yes. Hi. Hi, Heng. I have a question about this. The example where you said that we don't need to fill the cells behind on the diagonal where we already filled it. Can you show it again? I was surprised that we ended up with score 2 there. Why not 3? How did we end up with 2 while going, or does it show some weird connections in the graph? Or is it a linear?
You mean
linear example?
this?
No, the one that yes, this one.
Okay. This is, I mean, this is wrong. I mean, shouldn't be 3 here because it has already been calculated before. And so this, but if you calculate it again from here, this would be 3. But it's actually, this cell should be 1. You can see here, this is 1, and C and C, this should be 1. I mean, the correct answer is 1. But if you don't know this, if you don't remember that, you will recalculate at 3. But that would be wrong. And so this.
Yes, but how did we get 2 in the next cell in this diagonal in the?
You mean this cell?
On the main diagonal? Yes.
You mean this? This in the previous round it was 1. This you can see this 1, and so you do extension, then C and C equal the correct number. The correct answer is 1, and so here is 2. But if you recalculate that, I mean, this number actually, you calculate this cell twice. And actually, you got the wrong number in these cells. And so that's why we want to avoid doing the repeated calculation.
Right, I see. Got you. Okay, thank you very much.
Actually, I mean, even if you do repeated calculation, the answer is actually correct. I mean, because the space had moved along, already moved along. And so you will get the correct answer, but you will do repeated calculation. And that is actually quite wasteful. It's much slower if you don't, block these diagonals.
Got you. Thank you so much.
Okay, so I think we have two questions on the chat. So first, I take them by arrival time. Huh? The first from Regef, if I say it correctly, I hope it's the question is about SEMD. So with two-dimensional dynamic programming matrix, we can use SEMD. Is it possible with this approach with graphs?
We can't for the WFA. I mean, it's actually use SIMD, but use the SIMD in a different way. It's I mean, I would recommend to you to read the WFA paper about how they do the SIMD formulation. I mean, it's use automatic vector rationalization. This is possible. And for the graph one, actually, I forgot to mention that the graph one can be reduced to a linear one. If you have very long, sequences, it's reduced to linear sequences just within nodes. And so actually, you can the same SIMD tricks is also applicable as long as it's very long. But in this case, if you have many small nodes, that wouldn't work well.
Okay, and a question from Garance about the heuristic. So I guess it's a pruning heuristic she's talking about, and she asked on which kind of graph this may apply. So I don't understand perfectly the question, and maybe it's related to doubling graphs or compacted doubling graphs or any kind of graphs on which this may work.
This heuristic is actually it's a bit tricky actually in practice. It's if you know the right setting, there's we use Pern. Basically, for this way, this is the actually effectively the sequence lines in the alignment, and this is for the sequence line in the alignment, and you need to set a parameter between these two. Basically, how large you start to print. That parameter is actually tricky. If you set it wrong, you will get a wrong answer. You can get a very wrong answer if you set it wrong. And so in practice, actually, we just we use some number. Basically, we accept it's wrong. I mean, if it's wrong, we just accept it in the mini graph because sometimes it's very costly to find the best alignment. We just accept a suboptimal alignment in the mini graph. And in the mini graph, we always use this heuristic, this Pernian heuristic for all type of graphs.
We have another technical question in the chat, and someone raised his hand, but I missed it. So can you do it again? So waiting for this, I will ask the coder question. Ivan, okay, I saw you. So the coder question is how the best pass before GWFA is selected from the chains, given that we may get multiple seed hits.
How the best pass? It's the best pass only has two considerations. First is the base score of individual chains. You have score, and then you have a gap because you know the gravity distance. You can just say find the closest for example, between the the query lines between these two, and then you just try to find the path with similar sequence lengths to the query sequences. And then this is how you. It doesn't always work that well. Sometimes it may make me mistake. This is a problem with mini graph. And Jirac has a recent preprint on this topic, but basically it's a dot chaining on the graph. Here is a two-step chaining. First, chaining on the linear sequence and then on the graph. But actually, there's multiple other issues. And his chaining algorithm is basically directly doing just one round of chaining on the graph. And so it's probably better. But the problem is that his algorithm only works on a DAG, on a cyclic graph, not on a cyclic graph. So there's trade-off. So far, I'm not sure. I'm not aware of this efficient graph chaining, direct one-step chaining algorithm that works for a cyclic graph. It would be nice to apply that.
Okay, thank you. So Ivan, I think you had a question, or Ivan?
Hi. Yeah. First of all, nice presentation and a very interesting topic. So my question is actually related to this. I was just curious if minigraph does any sort of subgraph extraction before alignment, because there can be nodes that have 0 seed hits, and how do you do that in minigraph?
In the mini graph, when we do the graph training, I mean this linear training, graph training, this on the whole graph, and we do when we do the base alignment, when we start to apply GWFA, it is effective on the subgraph, but actually in the code is actually not extracting the subgraph. It's actually in the implementation is just specify the start position, starting base in the whole graph and the ending base in the whole graph, and then just apply it. But of course, the algorithm runs in the local graph, but we don't explicitly separate the subgraph.
Okay, thank you.
Okay.
I have another one, a bit technical again. I think maybe I missed it, but I haven't seen results showing the impact of the pruning algorithm on the quality of the results. And how you choose, I guess there is a parameter somewhere to prune or not to prune depending on.
Yeah.
And how can we choose this parameter, and do you know the impact?
That's a very good question and also a hard question. It's in practice actually it's not easy to know what's the best parameter. That's I think the problem. And if you choose the wrong parameter, you miss the, for example, the I mean especially on the G4 data set, say the optimal edit distance is 43,000. I mean in the first example 43,000. If you use the wrong one, it sometimes can even get a million. The edit distance million can be much worse than the optimal one. It's not a little bit worse, much worse than the optimal one. And in minigraph, we still, I think I'm using a number of 5,000. And if we can't get the optimal alignment, basically just give up. Okay, actually, I was wrong. If we can't find the best alignment within this say the cutoff of 5,000, we will reduce to approximate alignment. We basically just choose the alignment path with the closest sequence length. We don't look at the base sequence. It's reduced to a low quality alignment. So far, I don't have a solution on how to choose the best cutoff. It's a tricky one.
Okay.
In this example, we actually it's still relatively simple, and so actually it's in this example it's not that big issue. But when I apply the GWA integrate GWA into the mini graph, there are some cases. I mean, it's hard to find the best tuning parameter and pruning parameter.
Okay, thanks. There is again a question in the chat. So do you have, I read it, I haven't read it before. Do you have any comments on how the graph impacts the results or performance of the GWFA? Are there any desirable properties for the input graph? Minimum length of nodes.
In theory, it works on all types of graphs, but in practice, it would be better to have longer vertices, because I mean, in the longer vertices, it effectively is applying the linear, Ukkonen OND algorithm on the long vertices. So it's much faster than tracking the graph topology and traversing the graph topology. It's much faster than that. Catch misses and also all the possible optimizations. And so it's preferred that the graph has longer vertices. And also, I have also tried on doubling graph. It actually doesn't work well. It works. Only works when the edit distance is very small. I mean, I tried doubling graph on MDC haplotypes. They're actually a huge graph. And so it only works when the edit distance is very small. The reason is that the doubling graph has kind of similar but duplicated sequences all around in the whole graph. And so when we start to traverse the graph with the GWFA procedure, there are many nodes with small edit distance. And so you will traverse a lot of a large part of the graph. And in the end, it becomes much slower. And so again, works best on simple graph with very long vertices.
You were talking about doubling graph or compacted doubling graph?
I was talking compacted.
Compacted, okay. So this means that you have an implementation that works on compacted doubling graphs today?
It's actually, I'm not sure. I mean, I just, I mean, in my experiment, I just constructed a compacted doubling graph for all the MLC haplotypes, 60 something of them. Each of them have 5 megabase. I construct a graph on of that, and I align another different MLC haplotype to that. This actually takes off. It doesn't that it still works. It's just I mean too slow to be practical.
Okay, thank you again. Are there any other question? I do not see any. Ryan has raised his hand.
Yeah, hello, can you hear me?
Yes, we do.
Yes.
Excellent. Hi, Hank. It's a pleasure to see you talk. I think I speak for many to say when I say that. So I have two small questions. One is related to the terminology. So when you apply GWFA with edit distance, would it be accurate to say that this is essentially graph Ukonen?
Yeah, more exactly, yes. But I think these days, and when people talk about this diagonal like algorithm, I think people often just call it WFA because they don't distinguish the two. But more exactly, yes, you are right.
Yeah, I see. Yes, great, thanks. And small question about the README of MeWFA. You mentioned that it implements a dual gap penalty, and having issue finding definition of what a dual gap penalty is.
That's in the minimum paper. Basically, you have two sets of gap, two sets of FN gap. I mean, different gap open and different gap detention. And people use this mostly because to deal with the long gaps. The say structural variation. There's a structural variation, and usually this dual gap produce a better alignment. If you just use one set of gaps, I mean, like the standard FN gap alignment, I mean, it's once there are some say 5% single error rate, it often splits a say 300 base pair gap into smaller gaps. Say, I mean, 50, 100. 50 and 100 split into several gaps, and so it's makes it difficult to do the structural variation calling.
Okay,
so that's the main reason why we use why Minimap2 uses these two gaps. And the idea is actually is published in I think 1990, as I remember, by I think by Goto. I mean, the initial idea is from that. Actually, I came up with the idea independently, but I thought, I mean, there must be someone has already found the idea. And so I Googled around and found that paper. Indeed, I mean, so people have found it.
Okay, great. Just to be clear, this is a fine penalty.
The double affine, basically, I would say the multiple affine, piecewise affine gap penalty.
Okay. All right, sounds good. Thank you.
Okay. It's not really a question, but I was not able to find the supplementary materials on the archive page, so I don't know if I missed something or if they are not online, but just to be aware.
Okay, we will try.
And I see no more questions, so I would like
That
to...
is my question.
Okay.
Just, yeah, I mean, I think it will be the last. It's mainly an historical one. I mean, since the notion of wavefront goes back to almost 30 years ago, my question is, how do you explain the fact that it was almost ignored for many years? What is your explanation?
The reason is that, like what I explained, why is we didn't implement the FN gap penalty on the graph. It's actually quite challenging. Let me come back to this. With the I mean at distance, I mean the number 3 always adjacent to cell 2. It's always case. But if you have a start to have not at distance, I mean, you start to have even gap, even linear gap penalty, as you have the substitution matrix. Actually, they don't adjacent. And actually, it's difficult to keep track of this information. For example, I mean, with the, say with the even gap, I mean, this number 3 won't be here. Probably this is 5 here, and so it's not adjacent. It's a you need to keep a band to keep the score, different scores in this band to make it work. And so this made the structure much more complex. And so it's take quite a long time for people to realize how to do that. And I think the more important thing is, I mean, the WFA developers make it very efficient. That's another very important contribution. Is they use automatic vectorization. I mean, it's actually using the SIMD to do this and making it much faster than all the other, I mean, Smith-Waterman implementation. And so this makes this quickly popular in this field. It's very important work and very impressive, and it's engineering fit. I also learned a lot from the implementation.
And this means that we still have to read Yukonen's book. Okay, so thank you again. I think we can upload again. Congrats, thank you very much.